Okay, great. While we wait for others to join, I think it's time for us to already kickstart this webinar. So ladies and gentlemen, distinguished guests, colleagues and fellow experts, thank you for joining this important webinar on navigating post-harvest losses. I'm excited, apparently, and honored to be your moderator. And together with my esteemed colleagues, we aim to shed light on the critical issues that affect post-harvest losses with regards to food security, economies, and sustainability worldwide, and also proffer some solutions on how we can address these challenges. Over the next few minutes, we will delve into the causes, consequences, and most importantly, the solutions to mitigate these post-harvest losses. But before we do that, permit me to introduce our distinguished panelists. So first, I would like us to welcome Sonia Metilita. Sonia is the Chief Operating Officer at Solar Cooling Engineering, Germany, focusing on solar-powered cooling solutions for mainly the agricultural sector. With an academic background in tropical and subtropical agricultural sciences, she sees energy access as vital for a sustainable and enhanced food production. Solar cooling engineering empowers local firms to produce their own cooling systems, creating jobs and bolstering the value chain in target countries. It's nice to have you here, Sonia.
Thank you. Nice being here.
Great. So next is Josiane Cloutier. Josiane is a researcher in post-harvest technology at the Wageningen Food and Bio-Based Research Netherlands. Josiane has worked at Wageningen Food and Bio-Based Research in the post-harvest technology group since 2019. Before that, she has worked in several fields of agricultural sector, including as an agricultural advisor, biological control advisor, greenhouse manager, teacher in an international agribusiness business administration with horticulture specialization. She combines all these expertise in national and international projects in order to improve post-harvest handling processes and reduce post-harvest losses. Thanks, Josiane, for agreeing to be part of this conversation. Great. Let us welcome Tess de Vrije. Tess is a scientist at the Swiss Federal Laboratory, EMPA, in Switzerland, and also a professor at the Wageningen University, working in post-harvest technology. The goal of his team is to identify when and where the quality of fresh fruits and vegetables is lost. The tools his team develops are multi-physics simulations, various types of sensors, and data upcycling. This information is often used to help increase shelf life and prevent food losses. Thank you, Tess, for honoring this invitation, and welcome to this webinar. Great. And last but not the least is myself. I am Daniel Onwude. I'm an agricultural engineer and a scientist at the Swiss Federal Lab, EMPA, Switzerland. At EMPA, I currently lead your virtual coaching assistant initiative in Nigeria. Great. So now we've welcomed all the panelists. Before we start the panel discussion, permit me to take you through the journey of fresh fruits and vegetables once they are harvested from the farm. Now, imagine you have a bunch of fruit and vegetables from a farm. These freshly harvested produce are just like living things. They are alive, they breathe, stuff like we do. They give off heat, and they can even get sick or spoil. Fruits and vegetables can also start to lose moisture and freshness over time. All of these occur during the post-harvest journey from the farm until it gets to our table as the consumers. But let's see really what happens to these fresh produce once they're harvested from the farm. There are different steps and challenges they go through, which also depends on the value chain and the end product. The typical supply chain of fresh fruits and vegetables could be domestic or export supply chain. Consider oranges, for example. if they are to be turned into juice or other processed foods, and they are meant to be eaten domestically or locally, they go from the farm to a place where they are sorted and packed. After that, they might be cooled down and stored before they are taken to the factory, where they are turned into juice, dry fruits, and frozen fruits, and so on and so forth. Once they are processed, they are sent to the retail outlet, like supermarket or market for us to buy. But for fruits and vegetables that we eat fresh in the same locality, they go through similar steps. They are sorted, cleaned, and treated to be of good quality. Then they are kept in cold storage before they are sent to stores. The ones that are not good enough to be sold might go to the factory for more processing or be used as natural fertilizers back on the farm. Now, for export supply chain, for the fresh produce, after cold storage, they are often shipped in specialized containers with cool temperatures, just like the big fridge that we have in our homes, to stay fresh during the journey to different regions. On arrival in those regions, they undergo similar processes as the domestic supply chain, as I just explained earlier, before they get to the consumers. The processed food also follows similar pattern, where they are shipped in these containers to different regions before they reach to their final destination. Now, from this flowchart on your screen, you could tell that the supply chain of fresh produce is very complex. And to further depict the complexity of this supply chain, if you look at the video on your screen, the tiny yellow dots in this video represent the complex movement of tens of thousands of shipments across the world on a daily basis. This process is very complicated, and stakeholders in this value chain have to be very careful about temperature and other conditions to keep the food good. But because the quality of fresh fruits and vegetables, to be precise, changes over time, and also because of the challenges of storage and transportation, a whole lot of things go wrong with the supply chain. For instance, like the optimal storage conditions. Temperature, as an example, is a driver of this food waste. Too high temperature would lead to, for instance, accelerated quality loss or pest infestation, while too low temperature could lead to chilling injury. Also, we have the issue of relative humidity, where too high relative humidity could lead to a condensation or microbial growth due to condensation, and too low relative humidity could result to moisture loss. Apart from these drivers, we also have the issue of multi-commodity. We have issues waiting at the port or handling issues. All these lead to huge amounts of food losses and waste across the post-harvest supply chain. Now, this waste, in addition to the degradation of some nutrients over time, also means that we lose important nutrients in the food that get to us at the consumers, which can make us, of course, less healthy. All these losses also translate to loss in water, land, labor, and even capital. Now, the question is, how do we solve this complex issue? I would say to solve this key problem, we need to better preserve nutritious food and in this complex supply chain, and make sure that more people have access to this food. Now, to address this, there are several solutions, there are several methods that we could use to address this. But focusing on the low and middle income country, a promising approach to tackle post-harvest losses is the use of decentralized cold rooms near our farms and markets. Another effective strategy is by utilizing passive cooling systems for storing fruits and vegetables after harvest, right? However, these solutions remain underutilized, particularly in these low and middle income countries. So to gain a deeper insight into the reasons behind this underutilization and explore potential mitigation strategies, we will turn our attention to our esteemed panel of experts. And we'll, of course, take up questions and answer and try to answer them at the end of all the panel discussion. Great. Now, without much ado, let me start with Sonia. Maybe I'll stop sharing my screen in case you want to answer with yours, in case you have a presentation to share. Okay, I'll stop sharing my screen now. Great. Okay, so I will start with you, Sonia, if you don't mind. So I have a question for you. Just a moment. Yeah, so you could put up your screen once I ask the question if you like. So my question to you is, what sustainability and technical considerations should cooling providers prioritize when designing post-harvest storage cold rooms? And the second question I have for you is, what is the way forward for using cooling as a tool to fight post-harvest losses?
Thank you, Daniel, for those questions. Yes, do you hear me?
Yes.
And you see my screen too?
Yes.
Perfect, then I can start. Yeah, so I made a small presentation trying to answer those questions. No, it doesn't go on. Hold on. Let me try again. Somehow. Do you see the next slide now?
No.
No? Okay.
Yeah.
Let me try again. Now?
Yes.
Okay, perfect. Sorry for the inconvenience.
No worries.
So there are several general considerations that we need to look at if we look at cold room consideration, and you mentioned already quite a number of them. So an important one is to have product knowledge. These are the points that you have just mentioned. So what are the physiological processes that go on after the product has been harvested? What are the optimum storage conditions for each product, but also what's the growing cycle of it? So how often, at which times is the product being harvested? Then another important consideration is knowing the value chain. Who are the involved players? What's the own position and the impact in that value chain? And then what's the market development, and also considering the price development, because when we talk about cold rooms, we also talk about a considerable investment costs that have to be done to get this on the ground. And another one is the technical knowledge. So which technologies are available, what's their efficiency, and what's also their sustainability. And at this point, that's the point where I'm going to shine more light on now. So number one is what technologies are even available to cool a space. So there are refrigeration methods which are refrigerant free. Then there are others with refrigerant, and these are with and without phase change. And within the phase change, there are open circuit and closed circuit. And there, evaporative cooling and vapor compression are the two methods which are the ones mostly used for cold rooms. So evaporative cooling, that's basically when you use it's also called free cooling, because you take warm and dry air, and just by adding water to it, you get cold humidified air. That's also mentioned before in the picture with the charcoal cooler, and we're going to have a look at it in one of the next slides. What is vapor compression? That is mainly known by the people in the AC air conditioning systems that are being used in households and also in industries. And to compare the two technologies which are mostly available for cold rooms, that's the charcoal cold room and the vapor compression heat pump, in this case now with a thermal storage and a water heat air exchanger. And the advantages of the charcoal room would be that it can have lower costs because locally available natural materials can be used. It can be done in a DIY option. It is also energy dependent because it only requires water. As I said before, it's also called free cooling. And because you don't need energy input, you only need water to keep the charcoal wet. But a negative thing about it is that the temperatures are not stable inside the room. And the higher the relative humidity in your ambient air, the lower is the potential of temperature reduction. And now when we're having a look at the vapor compression heat pumps, they do have a stable and controlled conditions in the room. And you get a temperature range which is much higher than the one which you could get with a charcoal cooler, because you can get down to even freezing temperatures, or if you don't do a chilling room, but a freezing room, you can also get below 0. A thing is that it has energy requirements because it runs on electricity, the vapor compression heat pump, and it is relatively cost intensive compared to a charcoal cold room. But I also wanted to shine a light on the sustainability of it. In the vapor compression heat pump, the sustainability of the overall cold room can be improved through different choices and considerations. And one very important one is to use natural refrigerants like R600A or R290. And in many countries, using natural refrigerants is already a requirement or will become in the next years a requirement. This is due to the Kigali Amendment to the Montreal Protocol, which was made to reduce the CO2 footprint of the cooling sector. Another measurement could be to use insulation material from natural resources. This is still a bit at the starting point, but has a lot of potential too. And also to do local production to decrease the transport and strengthen also the local economy to become more overall sustainable. And as well to upcycle or reuse materials to become part of the circular economy and be more sustainable. And of course, modularity, because there is no one size fits all. So sometimes a system, if it's just a size X, then sometimes it can be for one application oversized and for another one undersized. And this is also not sustainable. Now, what would be the way forward? The important steps is to increase the efficiency, increase the sustainability, close the cold chain, and education. Now, to increase the efficiency, the heat pumps must be developed for the corresponding environments, because we're talking mostly about the tropical countries. So we are talking about high ambient temperatures. So therefore, the heat pumps should be developed to suit especially those climates, and thereby also increase their COP. And then also because most of the times, if we talk about the vapor compression heat pump cold room, then there needs to be energy available, and in every case, the best and most reliable and cost-efficient energy mix should be found. And then thermal storage can be added to increase the autonomy time and to save, if we're talking about a solar-powered cold room, to save batteries. The insulation material, which I had mentioned in my previous slide, is also an important way to increase the efficiency, because by the thickness and by also the material that's being used, because with this, through the adequate material with good thermal properties, the thermal losses can be reduced drastically. In terms of sustainability, a CO2 neutral cold room powered by solar energy is possible. At Selftrue, we are currently working on that to use as much natural materials as possible, as locally manufactured as possible, and with solar power as the power source. Another important stepstone is a closed cold chain, because an uninterrupted cold chain from field to fork is important, because cooling can never restore the product quality that has been lost already due to the lack of cooling. It can only maintain the quality. And therefore also variation in types and sizes of systems that suit the implementation point in the value chain is crucial, because it needs to, the size of the cold room needs to fit where it is along the value chain. At farm level, the size of a cold room will definitely be different rather than at port level or industry level. Another very, very important point always is education. So there must be education, just like this webinar now, about best practices on product handling and quality conservation, but also about the cooling requirements that one has and needs, and then to be able to evaluate the technical design considerations, see the market linkages, and also have financial literacy about the costs and the return of investment of a cold room. So that's it from my side. Thanks very much for this opportunity to talk here at the webinar. And if you'd like to know more, here are my contact dates.
Thank you so much, Sonia. Yeah, to the audience, if you have questions, please just use the Q&A button in your Zoom and just directly ask your questions. At the end of these sessions, we will take all questions and ask the panelists. Okay, great. Next, I have some questions for Josiane. The first question is, what are the best practices for cold room operators, particularly in multi-commodity storage? And then my second question is, how can operators determine the optimal temperature for multi-commodity storage?
Thank you, Daniel. Those questions are very good questions. I put them in my PowerPoint. Yeah, now it's working. So what are the best practices for cold room operators? And at what temperature do we have to store? It goes hand in hand, I think. The first question, and it starts with the temperature management. And actually, it depends what the situation is, but if the cold storage starts at the farm or near the farm, we have to take into account that it's a best practices starts in the field. So we want to minimize the temperature increase. Here I show an example of melons that were kept under the sun, as it shows on the picture on the right, and slowly the temperature increases, and you see the difference of temperature on the top and on the bottom of those chariots. And you see that between 10 and maybe 9-ish and 10:30-ish, we have quite an increase of temperature, and that temperature we will have to remove once it's at the cold storage. So if we could avoid this increase of temperature, it's also a lot of energy that we do not have to take out of the fruit. So tip number one is to avoid field heat buildup. So put the fruit under a shed, in the shadow, or leave it as short as possible in the field. So yeah, cold room, best practices of cold rooms starts in the field. But if we want to, let's say in a situation we do not have control what's happening in the field, then I want to sensibilize about the importance of pre-cooling. Because it's not only about cooling, but also about how to pre-cool. And here we show a graph representing the shelf life on the x-axis and the temperature at which the food is stored. If we use no cooling, the temperature will increase slowly due to respiration. If we use room cooling only, the temperature will decrease quite slowly, and therefore the shelf life of the product will be extended compared to no cooling, but much shorter than if we use pre-cooling. What is pre-cooling? Pre-cooling is to decrease the temperature of the product quite rapidly after arrival at the cold storage facilities to extend the shelf life. It also allows to separate what's already been cooled, that it's in a separate room, and what needs to be cooled. Because if we have products in one room at the target storage temperature, let's say 2 degrees, and we bring something in which is at 25 or 30 degrees, it will warm up the room, and then we have to take all that heat again. So the product temperature will vary, and we want to avoid that because the temperature variation in the storage will contribute to a shorter storage possibility and also shelf life. So tip number 2, use pre-cooling to extend the shelf life and reduce the cooling time to energy. But what is pre-cooling? So I show you a few examples. It can be to simply place the product in a cold room, which is only dedicated for the pre-cooling, and once it reaches target temperature, then it's moved to a storage cold room. We can also use plastic DARP to direct the air circulation to improve the circularity of air to cool down the product more rapidly. You also have forced air cooling, which is a common method. It's then you cover the product with plastic and you put a fan to really force air to go through it. Of course, you have to be careful not to overdo it because then you can also damage the product. In cases of more specific pre-cooling, we can use vacuum cooling as to work with pressure to remove the heat. That's done a lot with lettuce, for example. We can use hydro cooling, which is done a lot with carrots or cherries. Or we can use ice, which is often used for broccoli. In the first picture here, we see the result of multi-product storage. We see different boxes of different products that once they're at the target temperature, then they can be put in the same room. I will come back to it. A little bit more about the airflow, which I continue my talk more about optimizing cooling for the best practices, is that we want to prevent the false airflow. This is why that we put those plastic here to ensure that the cold air goes around the product and come back. Those this must be looked at and individually. Of course, there's like big rules of thumb, but it has to be designed for every individual. Cold storage, it will depend of the ventilation, of the refrigeration capacity, of the product itself, of the type of bins used. So all those factors will depend on how to prevent the false airflow. And lastly, you have to make sure that the air circulation is similar in the entire cold room. And we want to minimize the hottest spot and the coldest spot to have a uniform condition for the products. Another thing that we can think of while doing the best practices in a cold room is that we want to have the right refrigeration capacity. To reduce energy consumption can be achieved by having the right capacity. And then depending what type of free cooling you have and what is the heat field that you have to remove and so forth, and the temperature at which the product needs to be stored and how long it needs to be stored. It depends if we're talking about long storage or short storage. I will come back to it. Then you need a certain refrigeration capacity. And you can compare it to a car. If you want to save on your car and you buy a smaller motor, because the smaller motor will consume less, but you are in a very hilly environment, then you will lack power for your car to climb those hills, and therefore you will end up using more energy than if you would have a more powerful motor. So this situation could be transferred a little bit to cold rooms, that sometimes it could be better to have a higher refrigeration capacity, and if you have too little, then you end up having too many cooling actions. It's in the list here, because you want to reach that sweet spots of optimal cooling actions, which is about 24 per day. So if you end up doing more per day, then you will create more ice on your evaporator. Here, defrost once a day. And if you create more ice, then you will have to defrost more than once a day, which is also producing heat. And therefore, you will have to use your ventilation fan, which also produces heat. So I don't know if you kind of start to get in what you're getting into. So having the proper refrigeration capacity allowed to have the proper number of cooling actions, and therefore the defrosting, and you minimize the amount of heat that you bring into your cold room. Here on the right, I show a pie to show the proportion where the heat in the cold room come from. And talking about reducing heat, we want to also reduce the ambient temperature, meaning that if you could isolate your cold room, that would be even better. What I mean is to have a cold room within the building. And also in some circumstances, it might be also good to even cool the space of that building. So around the cold room and the attic and the and where you walk, to then also reduce those cooling action you need, and to bring a more stable condition in your cold room. And then to optimize the cooling, well, you have the running of the refrigeration, but also the maintenance. So you want to keep it clean, you want to keep it intact. Don't forget that pellets and beans can also create dust, and that dust will end up in your refrigeration system. So you want to keep it clean, to keep it as efficient as possible. It seems very logical, but it is unfortunately often forgotten. So keep it clean on a regular basis. And now that brings me to the second question, which was, how can we operate a cold room at the optimal temperature? And the question was also for multi-commodity storage. So I will talk about both only one product per room, and then multi-commodity storage. To look at the optimal temperature, you have to, of course, look at the crop. And if you store only one produce, then you may look also at the variety and also at the maturity level. And you may have to take into account the ethylene management. Do you use an ethylene blocker for products that produce a lot of ethylene, which is responsible for ripening? And are you cooling only for pre-market? That meaning that after 1 or 2 days, your produce will be moved to retailer or be sold, or do you want to store for a long time? So you have to define also those 2 goals, because that will also define how you will use your cold storage. And then in a setting of a multi-commodity storage, best case scenario, that would be to have at least 3 rooms. It's not always possible, but if it is possible, then you have a room that should be between 0 and 2 degrees for temperate products. Think of apple, pears, broccoli, cabbage. You have to have also a room for between 8 to 10 products for subtropical products. Think of citrus, avocado, maybe unripe mango. Yeah, and then the tropical products, 12, 14 degrees for bananas, ripe mango. Yeah. And if you do not have the luxury of having 3 rooms at 3 different temperature, well, of course, then you have to compromise. So maybe 4 degrees could be the best scenario you can do, except for the bananas, you cannot do that. But for the other products, maybe they can, the subtropical products, they may survive 4 degrees as long as they are there for a very short period of time, meaning that they will not reach that 4 degrees. So meaning that they are coming from somewhere else, that they are stored at 8 to 10 degrees, and you bring them at that cold room for a short period of time, which is at 4 degrees. So it will take some time for them to go to 4 degrees. And then you might keep the quality without any chilling injury. And the chilling injury is when the fruit is exposed to a too cold temperature and the quality of the product will degrade. Finally, in a multi-commodity storage, you have to be aware of ethylene management. So you don't want to mix or put products too close to each other that are sensible to one another. For example, apples and broccoli, they go very well together in terms of temperature. But if they are stored together, the ethylene produced by the apple might degreen the broccoli. So your broccoli will become quite yellow quite fast. So then, yeah, that's something to take into account. And maybe something more practical, garlic and mushrooms, they don't go well together, but it's more because then your mushroom will taste like garlic, although when you cook them, mushroom and garlic goes well together, but you don't want to sell them this way. So yeah, so those are practical tips. If you are interested, we have an application for long storage of cold storage of apple and pears that we developed. We give advice via this this application. That will give you the temperature in your cold storage that you need to reach according to the crop, the variety, when it was harvested. Do you use the ethylene blocker? In this case, that's the 1-MCP. What CO2 level do you have to bring your cold room? What oxygen level you have to bring cold room? And for apple and pears, the moisture loss is managed, and you want to lose a little bit of water for apples per month, and for pears, you want to limit that. So we give a advice. If you are interested, you can also contact me. So in conclusion, I wanted to wrap up what I just said. Avoid field heat buildup, use pre-cooling, use the refrigeration capacity that fits your need. Make sure you optimize cooling and your cooling actions, and you use good maintenance, and how to determine your temperature, the optimal temperature for your what you're storing. Then you have to look at which crop you're storing, how long and make either compromises or make uses of several rooms. Feel free to contact me. We also have a website, freshknowledge.eu, where you can find a lot of free information. And that closes what I wanted to explain.
Great. Thanks, Josiane. Super interesting. I actually always find the whole idea of a multi-commodity very interesting, considering that we know that most smallholder farmers may not be able to have different rooms for different crops. So please feel free to send your questions, write your question down in case you have any question for Josiane. And then we move to the next panelist, Tess DeFraye. So I have a couple of questions for you. I'm sure Josiane and Sonia have touched a bit about these questions, but maybe it'd be nice to also hear from you. What factors influence the positioning of crates within a cold room? And how can we envision a crate arrangement in a multi-commodity room to ensure that crops are tolerant of warmer temperatures are placed in the appropriate warmer areas, while those requiring colder temperatures are positioned in cooler spots? The second question is active cooling always the answer? Or are there situations where passive cooling solutions should be explored? It would be nice to also get examples of passive cooling options.
Yes, Daniel, thanks a lot for your questions. Happy to be here. So I'll try to give a glimpse to you on at least my vision and my view on these problems. Josiane and Sonia touched on these aspects already. So first question would be, where are the warm locations? Where are the cold locations in such a cold storage room? I will focus mainly on the small ones, which smallholder farmers or FPOs, let's say, can use. So you see here in the image on the right side, an example of a real cold storage room, and on the left side, you see another example of a smaller cold storage room. So very important to answer this question is to know where these warm and cold spots are, and this all has to do with airflow. So you see on the left and on the right these fans appearing. So they're normally close to the refrigeration unit. So normally they blow cold air inside this cold storage room. You have different designs. Sometimes the fans are placed, as you see, in the center, on the right side, or on the top, on the left side. So this has a very big impact on where the cold air a little bit goes. And what is also very important is how your cold storage room is loaded. So if you have it fully loaded, the airflow pattern completely changes. So the, let's say, worst location for, let's say, warm temperature changes. When it's half loaded, as you see on the right side, the airflow pattern is a little bit more difficult to predict and so on. So this all plays a very important role. Another thing is that you can also have airflow bypass, so that the air exits these fans and then finds the shortest route to the outlet. So then actually your cold air does not even touch some of the produce. So these are all aspects which play an important role. Last thing I want to say, and that's very important because we're talking about we cannot have warm locations in such a cold storage room. We should have everything cool. That's true, but there was also a question in the chat on this. So the worst location is not necessarily the warmest location, because depending on the produce you store, cold temperatures can also damage some of the produce. You can have chilling injury. Or the worst location for warm temperatures might not be the worst location for mass loss. So these are a little bit different angles to look at. So you can only not look at temperature as such. You should look at warm temperatures, cold temperatures, and also mass loss, for example. But in a nutshell, if you look at this cold room, let's say on the right side, and you see these fans blowing this air, let's say through the middle, what you would say is that the worst location would be very far away from the fans, very far away from the cold air. So that would be typically, intuitively, the worst location. It all depends a lot on, let's say, the loading and so on. Another thing, and that Josiane already mentioned, is, of course, if you have a lot of cargo which you load warm in this cold storage room, this will affect the entire temperature distribution. So it's not only airflow, where does the cold air go? It's where did you already store some heat, or where is the cold produce located? So this also affects how it's cooled down. So the issue is that often it depends on which cold storage room you look at. Often you don't have too much space to move. So if a new harvest comes in, a few new crates, then it might be difficult to move everything around. So everything is at the coldest location to cool it down as fast as possible. So this can be one other challenge you have. What's the solution? Well, the solution to understand where is the, let's say, coldest, warmest location or the driest location, if you look at mass loss, would be to measure. So you have to put some sensors inside. There is no way around it. So we do a lot of numerical simulations to look at airflow, heat transport in such cold storage rooms. That's all nice, but you have to measure in practice because it also depends on, let's say, loading, on packaging, and so on. So that's one solution towards understanding your cold storage room better, your cold storage room, because they're all a little bit different. And then what you can do to improve this, if you, let's say, for example, find some locations with where the temperature is a little bit warmer than others, then Josiane already mentioned you can use, for example, these airflow guiding devices or tarps to direct the airflow a little bit. Often you're very constrained in the space or in the options you have, because these storage rooms are often packed kind of dense, so you don't have too much access. But that's one way to improve it, like they do in industrial pre-coolers. They also use tarps, for example. And a very important thing is also not to load too much at once, because as Josiane mentioned, the temperature can just go up. So this is often difficult to control because you harvest when the time is right, but that's another aspect you could do. Then I touched now on airflow. One very important thing I want to show to you, and then we can go to the next slide, is the importance of packaging. So you saw these different plastic crates, that's true. So the design of these crates has a very big impact on how fast you can cool down. And this is often an underestimated aspect, I would say. So here you see, for example, cooling profiles, which we did on one single pallet of this, in this case, citrus fruit with a certain type of package. We put a lot of sensors inside, and you see these cooling profiles. So you see the temperature going down. It was a step down cooling. And then you see, depending on where they're located, these sensors or the fruit, then the airflow coming in and coming out, this completely gives a different cooling behavior depending on where the airflow comes in. So that we see that the fruit on the inflow side from the airflow cool much faster than on the outflow side. So it depends where is your fruit located compared to the cold air coming in. If we then would change the packaging, and that you see on the next slide in a way, or the next, then you see if you use another type of packaging, which is more open on the top, the cooling profile completely changes. So depending on which package you use, which crate you use, you can actually cool down your fruit much faster or much slower. So that's a very important aspect to consider as well, because these are things you can change. You can make sure that you use a certain type of crate, which is a little bit more open and so on. Still, the solution is measuring. That's actually very important. So that was a little bit my insights for the first question. With respect to the second question, is active cooling always the answer? Or can we maybe use passive cooling? Well, Sonia touched already on this in a very nice way, showing the different options. So I would like to add on this that indeed, I mean, active cooling has a lot of advantages. If you need consistency, and if you have rather large volumes, which you need to cool down very fast, so very perishable products, if you need to have a constant supply, if you don't want to have too much risk, then active cooling would still be the best way to go, I would say, from my perspective, although of course it has a higher, let's say, environmental impact. This is all nice, but there is a price tag on this. You have to, as Sonia mentioned, you have to buy the unit, you have to service it, you have to be able to access it, you have to have enough parts so it runs the entire year. So this is possible for, let's say, FPOs which have, for example, a little bit of more capacity. On the other hand, if you want to have a more do-it-yourself system, then you can use passive cooling, for example, as Sonia showed some examples. You can also have very big passive coolers, as we saw. A pioneer there is, let's say, MIT D-Lab, so they do a lot of nice work, amongst others in Africa. So passive cooling is a way to do it yourself in a very fast way with less, let's say, a little bit less success. You can cool not so fast, and it depends a lot on the climate you put it in. So if you want to deploy passive coolers, and we also did some research on this, where the best locations are to deploy them, it's very important you look at what is my local climate. If it's too humid, it likely will not work so good. If it's too cold, it likely will not work so good, because your temperature drop you can get compared to the ambient will not be so high. So very important, decide very well if the location you want to use your passive cooler is the right one for you, if you can get a big enough gain from passive cooling. And then you can build it in any type of size you would like. It can be as large as a refrigerated container, so 40 foot, 20 foot. You can also make very, very small ones, as Daniel showed in the beginning. You can even have these evaporative coolers, which are these Zier pots, so very, very small, just to put a few fruit and vegetables inside, but they work. So that's just physics. They work. You just have to put them in the right climate. So all of the things I just mentioned, Base made together with us also an operator's manual where all these guidelines are there. So you can also look at our website and download it from there. There are some insights of all the nice things we did. And this is only one piece of the puzzle. But thanks for listening. And if you have questions, please let me know in the chat or also contact me later. Thank you. Daniel, back to you.
Thanks, Tess. Really, really nice insights about multi-commodity and also the passive cooling concept. So we have a couple of questions here. Maybe I'll share my screen quickly. I'm not sure if we could take all of it or rather all of them. Tess have already answered some of the questions. Thank you, Tess, for doing justice to those few questions. But I would like to maybe ask the panelists some of the questions from the audience. One maybe to Sonia, to Josiane. One of the questions that came through is what steps should be followed to minimize condensation on the surface of a commodity when putting commodities in cold storage and when taking them out of the cold storage? I repeat, what steps should be followed to minimize condensation on the surface of a commodity when putting commodities in cold storage and when taking them out of cold storage?
Yeah, then that would be to pre-cool the product before pack them, because if we first pack them and then cool them down, and depending on humidity level and temperature, but that can create condensation in the product. So it depends. I don't know if the question is for packed or unpacked products. Otherwise, it would be to have a good airflow to minimize the deposition of water in the products. And when removing the products from the cold room, yeah, that is a challenge. And then to have again enough airflow to reduce water deposition on the fruits. That's to my knowledge what I can see to minimize the condensation.
Great. Yeah. There's another question for you also, Josiane. As temperature is considered in post-harvest losses, do we also need to consider humidity? I mean, I touched on this a little bit when I presented, but yeah. Do we also need to consider humidity? Does humidity also need to be controlled?
Yeah, in many cases it has to. Every commodity also has a optimal range of relative humidity. For example, for lettuce, you want to have it close to 100, between 95 and 100. And for other products, it won't be so damageable to have a lower relative humidity. If there's a big skin, for example, mango, but then you don't want to go too low. You don't want to go to 30, 40%, because then your product will lose water and shriveling will occur. So yes, the management of humidity is important. If your humidity is too low in your cold room, you can wet the floor. If you don't have access to high-tech technology, wetting the floor can be enough in a lot of cases. But then we have to make sure for safety of workers not to fall.
Yeah, true. No, great. Thanks, Josiane. I have a couple of questions for Tess, but maybe I would like to ask you, because of time, maybe just one. Tess, the question is the use of paper crates with customized holes better than the plastic crates, which is more or less fixed design with limited option for customization? Also, any recommendation developed for the crates designed for different commodities?
Yeah, so normally you would not use cardboard in a small room for, let's say, smallholder farmers. You use it for export often. So you would use in these cold storage rooms, I would say plastic or wood or another type of material. It has a lot of other advantages, but you can use the same design guidelines as we have for paper or cardboard packaging. So the idea is to ventilate as much as possible, knowing that if you make it very open and so on, that the airflow also can change. So making it super open is not necessarily the best way forward, because you can change the entire airflow pattern. So you have to design your crate or use the crate for which your cold storage room has been designed. Same with the pre-cooler. If you make it too open, the unit stops to function in a good way because the fan actually has not enough resistance, for example. So it's case by case.
Yeah, indeed. Thanks, Tess. There are a couple of questions that we can't answer now because of time limitation. So I would suggest that maybe would answer the questions and send it to the questionnaires. But also you could directly send your questions to each of the panelists. I think they provided their email address in their slides. Or if in case you don't know, you don't have an email address, you can also direct the questions to to Base via the channel on LinkedIn. Or also you could directly send it to us here. Great. Now I'm excited to announce the launch of our new operators manual, which is a collaborative effort between Base, EMPA, and local cooling companies in India and Nigeria. Tess mentioned about this a little bit, where you could find a lot of nice things that we did. So all this information we compile them in an operators manual. And there was one question that was asked about the optimum temperature for storing fruit. So all these are also in this manual. So you could also see some of the answers to your questions once you are able to download this manual. So this manual can be accessed via the barcode, or you could go to our website, www.yourvcca.org/documentation. So please feel free to download this manual, and I can bet you most of the questions that you are pondering upon have been answered in this manual, especially the issue of multi-commodity. We attempted to also provide some insight on the way to go with regards to smallholder farmers that store several multiple commodities in a cold room. Great. I think we are running out of time, so I'll probably end this now. Thank you so much, Tess Defraye from EMPA, Switzerland, Josiane from Wageningen Research from in Netherlands. Thanks, Sonia from Solar Cool Engineering, Germany. Thanks also for the great team behind the scene. Simran from Base, Selena from Base, Roberta from Base, all the team from EMPA that compiled the very, very nice manual, all the team from Base, Roberta, Thomas, thank you guys for very nice work. And please, for the audience, feel free to ask us any questions, just send an email, and we'll be glad to answer them. Thank you so much.